So 1, 2, 3, and 4, we're solving these equations, and you'll notice that the instructions say find the angle or angles on the unit circle. Yesterday when we were evaluating inverse trig functions, we were restricted to certain quadrants, and that's just by how those inverse trig functions are defined. Inverse sine is defined as having output values only in fourth and first quadrants, from negative pi over 2 to positive pi over 2. And it's defined that way because to have an inverse, the original function has to be 1 to 1. And as we saw, we have to restrict the original function sine to have a domain from negative pi over 2 to pi over 2 so that it would be 1 to 1 and therefore would have an inverse, and its inverse would be inverse sine. And therefore, the output values, instead of output values, the range for inverse sine has to also be between negative pi over 2 and pi over 2, which restricts it to the fourth and first quadrants. And then similarly for cosine and inverse cosine, tangent and inverse tangent. But for solving equations, we're not really using an inverse trig function. So we're not bound by those restrictions on the output values for inverse cosine, inverse sine, and inverse tangent. So we really can find all of the angles that are on the unit circle that would satisfy this equation. So in number 1, as we look at that equation, cosine of x equals -1, we know what it really means is find the angle or angles on the unit circle where when I take the cosine of that angle, I get -1. So it's similar to inverse trig functions. We're still using the value to find the angle. It's just we're not bound by the restrictions on domain and range that we are when we're dealing with an inverse trig function. So where on the unit circle does cosine take on a value of -1? Right here at pi. Right? So when we solve this equation, x is going to be equal to pi, because if I take the cosine of pi, I'm going to get -1. Is that the only angle that cosine has a value of -1? All right, it's the only angle between 0 and 2 pi, right? If I only go around the unit circle one time. But if I don't restrict myself to just going around the unit circle one time, I could go around as many times as I want, then any angle that's coterminal with pi would also be a solution, right? So how did we represent that previously? Good, plus or minus 2 pi n. And so pi is a solution, and then any angle that is coterminal with pi, which I would obtain by adding 2 pi or subtracting 2 pi n numbers of times. That would all produce angles whose cosine value is -1. All right, everybody good on number 1? All right, number 2, we have the sine of x is equal to -√2/2. Again, I'm not restricted to the specific quadrants where inverse sine is defined because now I'm finding all the angles on my unit circle. In what quadrant or quadrants will sine take on negative values? So I like to mark those as a reminder to myself that I am going to get 2 answers here, and my answers are going to come from the third and the fourth quadrants. At what angle, or what's the reference angle where the sine value is √2/2? Pi over 4. That would give me an angle in the first quadrant, and I've got to have answers in the third and fourth. So what's the corresponding pi over 4 angle in the third quadrant? 5 pi over 4, got to be a little bit bigger than 1. And then the corresponding pi over 4 angle in the fourth?
7 pi.
Right, almost 2. And all of the coterminal angles with each of those. Okay, on 1 and 2. All right, number 3, the tangent of x is equal to -√3. Get an equation to solve, and I'm looking for all the angles on the unit circle where tangent first just takes on negative values. What quadrants would that be? Second and fourth. Okay, so we're going to pull answers from the second and the fourth quadrants. What's the reference angle where tangent has a value of √3? 60 degrees, which is pi over 3. So let's get the answer in the second quadrant.
2 pi
And then the answer in the fourth quadrant? 5 pi. And so remember, in the second quadrant, you got to be a little bit less than 1. So if our denominator is 3, then we're going to do 2/3 pi. In the third quadrant, we would have to be a little bit bigger than 1, so that would be 4/3, although we're not getting an answer in the third quadrant here. And then in the fourth quadrant, we got to be close to 2, which would be 6/3, so that's 5/3 pi. And then all the coterminal angles. And then finally, for number 4, this looks like an equation where maybe it's already been factored for us. Oh, yeah. Yeah. Nope. Okay. So number 4 we have, it's like, already factored for us in a sense. And what we know when we have something that's in factored form equal to 0, then that means that either 2 cosine of x plus 1 needs to equal 0, or tangent of x minus 1 needs to equal 0. Which on the left-hand side would tell me that I would need cosine of x to equal -1/2, and or tangent to equal +1. So we just have 2 different equations that we're solving that's going to all contribute to the solution to the original equation. In what quadrants does cosine take on negative values? Second and third. And at what reference angle does cosine have a value of 1/2? Pi over 3. And 60 degrees, which is pi over 3. So for cosine of x equal to -1/2, we're going to get 2 pi over 3 and 4 pi over 3, along with all of the coterminal angles with those 2. And then what about when tangent's positive? First and third. Right? At what reference angle does tangent have a value of 1? Pi over 4. And that is in the first quadrant, so I'm going to tack on to the answers I already have. Pi over 4. And then what's the answer in the third quadrant?
So could you do like pi over 4 and then negative 3 pi over 4?
You could. Yep. That'd work. Okay. If I get on 1, 2, 3, and 4. All right, and we're going to do a lot more with equations starting, if not today, certainly on Monday. But we're going to go over all of our homework that we've accomplished so far this week. And part of that homework, I know we're going to be doing some verifying identities. And here's an example of verifying some identities. We have secant over secant minus tangent equals secant times secant plus tangent. Of course, when we see the instructions verify, that means that we've got to make the 2 sides equal somehow. I don't see anything squared, so my Pythagorean identities are out for right now. Any thoughts? Okay, let's see what that does. If we multiplied or distributed in secant, we would get secant squared x plus secant tangent. Then what do we need to do? We could make secant squared 1 plus tangent squared. I don't know if that's going anywhere. Okay, so if we did, so we have secant over secant minus tangent. So if you're saying if we multiply by secant plus tangent,
Oh, and then secant squared and tangent squared was 1. So be over 1.
so distribute this secant in, and that would give me secant squared plus secant tangent over, and then the denominators, multiplying those conjugates would give me secant squared minus tangent squared. What is secant squared minus tangent squared equal to? So 1 plus tangent squared is equal to secant squared. So if I subtract that tangent squared over, then secant squared minus tangent squared is 1. So actually, I don't even need to make that substitution. I could have left it as secant squared x, because now if that denominator is 1, then I get secant squared x plus secant tangent equals secant squared x plus secant tangent. I did it. Nice job.
Wait, so did you really think it wasn't going anywhere and then you was like, psych?
Yeah, I wouldn't have done it that way. But it's definitely a lot faster.
It's funny, they said they're like, lots of a lot faster.
So what did y'all do? Change everything to secant?
Yeah.
And sine and cosine?
The sine, well, the cosine on the sine of x plus cosine of x equals 1. That's the easiest one for me.
Yeah.
Sine squared plus cosine.
Yeah, that. I won't get squares.
Yeah, that would have worked. And I don't think it really would have taken a whole lot of time to do that if we had changed everything to sine and cosine. Secant is 1 over cosine. This secant's 1 over cosine. Tangent sine over cosine. And then I'm going to skip a few steps here, but if I had distributed in the secant first, I would have had secant squared plus secant tangent, and that all would have become 1 over cosine squared plus sine over cosine squared.
Yeah.
And then here, I have a compound fraction, so I'm going to multiply everything by the common denominator, which is just cosine. So I would have 1 over 1 minus sine. And this is 1 plus sine over cosine squared. And as soon as you rationalize this 1 minus sine on the left-hand side, then the two sides would be equal. That works. Everybody good on A? Just remember on these verifying that we all know what the final end is going to be. The final end is the two sides are equal. Now, ours in this example would look a little bit different than William's final product, but in the end, the sides are equal. No matter what, they might look different, but they're equal. So we all know what the end result is going to be. The work, the part that I'm going to grade is your steps along the way. So you've got to be real clear about your steps. I want to see how you changed everything to be in terms of sine and cosine. Or I want to see how you multiplied to get rid of a compound fraction and then multiplied by the conjugate. Or in William's case, just distributed in the secant and then multiplied by the conjugate. Okay? So as long as I got to be able to follow how you went from one step to the next. Okay? So it does take a little while to show all that, but that's really the actual graded part.
Do we have to let you know that we used an identity, or is it understood?
No, like in the example where, like here, when you multiply out, you'll have 1 minus sine squared, and then the next line you write it as cosine squared. I got it. Yeah, I don't need you to write that off to the side unless you want to.
So it doesn't matter if you get different results in the end, as long as you're equal.
Yep, I'm gonna, when I grade this, I'm not even gonna bother what the last thing says. I'm gonna start from the top and go through your steps. Because we could have a bunch of different ways that it looks like in the end, as long as the two sides are equal. All and then for B,
No,
Yeah, that was fine. I can't do that.
this is tough.
Yeah, I erased it.
All right, let's see. Well, I think, whenever we're faced with one where we're really struggling, just change everything to sine and cosine, see what happens. Tangent, we would write it as sine over cosine. Cosecant would be, if I go ahead and distribute it in, cosecant times 1 is cosecant, which is 1 over sine. And then cosecant times secant is 1 over sine times 1 over cosine, so that's 1 over sine cosine. All right, on the left-hand side, we have a compound fraction. So what do I need to multiply everything by to get rid of the little fraction? Cosine. So that's going to leave me with sine over cosine minus cosine squared. And what are we going to need to do on the right-hand side?
Multiply the second one by cosine to get a common denominator.
All right, get a common denominator, so we multiply this first fraction by cosine on top and bottom, and then we could add the two fractions together, so it's going to be cosine of x plus 1 over sine times cosine. Nothing cancels yet.
I thought about factoring the cosine x plus cosine, but that doesn't.
What's that?
I thought like maybe you could factor cosine x, but that doesn't really do anything.
Yes, it is. I did this one.
All right, multiply by sine.
Yes.
All right, there's several different routes that you could take at this point. Lindsay is being real creative here. All right, she said that what she wants to create is a sine squared in the denominator. Okay? And she'll tell you, I think I know what her plan is here, but what was your reasoning for doing that, Lindsay?
You can get perfect square with, like the sine squared x will turn into 1 minus cosine squared x, and then you can factor that out and cross that out.
All right, so that took a whole lot of forethought, was if I can create a sine squared in the denominator, then I know that sine squared is equal to 1 minus cosine squared. And 1 minus cosine squared is the difference of two perfect squares, where one of its factors is 1 plus cosine x. And that would cancel out. Okay? So I took some forethought, but it's going to work. The other thing that I think she was thinking was, at some point I got to have a sign in the numerator anyway, because there's a sign there. So I'll go ahead and just multiply the numerator and denominator by sign. I put the sign in the numerator. I can replace sine squared, this sine squared in the denominator, with 1 minus cosine squared. Then that's the difference of perfect squares. Which, in fact, yeah, 1 minus cosine squared. So I would factor into 1 minus cosine and 1 plus cosine. And then 1 plus cosines cancel. And, if we were to bring down this side over here on the left, then I have a sine of x in the numerator, and I can factor out a cosine in the denominator. I'll have sine of x in the numerator, and then cosine times 1 minus cosine in the denominator, and those two sides are equal.
So it doesn't have to be simplified whenever you're verifying.
Nope.
You don't have to say like tangent of it.
No. All you gotta do is get the two sides equal.
Yeah.
All right, let's see what else we got. I mean, that's one way for sure. You know, there's not an easier method. It's because the easiest method is the one you see. So, you know, if that's the one Lindsay saw, then that's the easier method for Lindsay. Another option would be, you know, up here we have cosine of x plus 1. So I could multiply by the conjugate of that. So that would give me, in the numerator, cosine squared minus 1. And in the denominator, we have sine of x, cosine of x, and cosine of x minus 1. I just don't want to distribute all that in. Yeah. You're going to tell me about cosine squared minus 1. It is. What else can you tell me about it?
It means sine.
Oh,
X
yes.
It's close. It's, you know, we start off with sine squared plus cosine squared equals 1. So if I subtract the 1 over, I've got to subtract the sine squared to the other side. So cosine squared minus 1 is really negative sine squared. Miss Stacy's room, we're maybe not. So that's a negative sine squared on the top. All right, then what? Yep, this sign in the x in the denominator can cancel with one of the ones in the numerator. And I could take this negative and move it down to the denominator. So my sine of x is going to be positive in the numerator. And then my denominator, if I distribute that negative in, now the 1 is positive and the cosine is negative. And those two sides are going to be equal. So doesn't matter to me either way, whichever way is easier for you. You know, and another option is, let's say right here, if you left this as cosine times 1 minus cosine, then you could have multiplied by the conjugate of this 1 minus cosine. That would have worked as well. Okay? So you got several options that'll get you. Are you there questions on your class starters? All right. Well, let's take out the homework from Wednesday night with all of the simplifying and verifying on it. Right. What about the 4 simplifying problems? Any questions from those 4? First 4? 1, 2, 3, 4? 3?
or just like when you go get to them together.
All right, so for 3, we have 1 plus secant over sine plus tangent. We can rewrite secant as 1 over cosine. And we could rewrite tangent as sine over cosine. I don't have anything squared, so I can't really use any of the Pythagorean identities right now. Once we've changed everything to sine and cosine, now I've got a compound fraction. So what's the common denominator? Cosine? That'll give me, in the numerator now, cosine plus 1. And in the denominator, I'm going to get sine cosine plus sine. Everybody good so far? All right, now what? Yep, there's a GCF in the denominator of sine. And once I factor out that sine, then I have cosine of x plus 1. And you'll notice the cosine of x is plus 1 cancel out. So you're left with 1 over sine, which is cosecant. All right, so number 1 is supposed to be cosecant. Oh.
I got two signs. I got
All right, number 2 is cotangent. We just did number 3. And then number 4 is sine x, cosine x.
So I can make you do number 1.
Number 1. We have sine of x plus cosine times cotangent, and cotangent is cosine over sine. So this really becomes sine of x plus cosine squared x over sine. And if I wanted to add those two fractions together, what would the common denominator be? So it would be sine squared over sine plus cosine squared over sine. And then when you add these together, you get sine squared plus cosine squared in the numerator, which is 1. And 1 over sine becomes cosecant.
Did you get two signs?
Yeah, it was because,
Sign over x too.
yeah, I messed up on the cotangent.
Oh, but it was so much easier if you did that, right? Anything else through 4? Number 4? All right, we have 1 over tangent plus cotangent. So tangent would be sine over cosine, and cotangent cosine over sine. And now we're dealing with a compound fraction. What is the common denominator for the little fractions?
Sine x, cosine x.
So I'm going to multiply 1 times sine cosine. I'm going to multiply sine over cosine times sine cosine. And when I do that, the cosines would cancel, and I'd be left with this sine times this sine, which is sine squared. And then I'm going to take cosine over sine times this common denominator, and the sines would cancel, and I'd be left with cosine times cosine, which is cosine squared. And it turns out that in the denominator, I'm left with sine squared plus cosine squared, which is 1. So I just get a numerator, which is sine cosine. All right, how about any questions through 8?
I just think eight.
The answers is
Yeah, you just make each other.
It's really not an answer.
That's why you asked if it was like 1 through 4. I was like,
All right, we have 8's kind of a fun one, really, because it has all 6 trig functions. Okay? Because cotangent minus tangent over sine plus cosine equals cosecant minus secant. But none of them are squared, so Pythagorean identities are out. So even though we do have all 6 trig functions, let's just change everything to be in terms of sine and cosine. So what's that?
That's what I think.
To change everything to sine and cosine.
yes, that's why.
I feel like that's like their lunch of those.
Well, at least it makes you feel like you've accomplished something, you know?
This is as far as you get. Now, how many points do you get if we do that?
1 if I feel generous.
That's good.
All right, so I've changed everything to be in terms of sine and cosine. One of our hints is to work with the more complicated side because there's more to do. And I think in this case, the left-handed side probably has a little bit more complication to it because it's a compound fraction. So let's multiply by the common denominator of the little fractions, which is, all right, sine of x, cosine of x. So sine of x, cosine of x times that first little fraction, sines cancel, you're left with cosine squared. Sine of x times cosine of x times the second fraction, the cosines cancel, and you're left with sine squared. And then here, you can distribute it in if you wanted to. I'm just not going to. Anything else you want to do with the left-hand side? All right, the numerator is the difference of perfect squares. Now be careful, the numerator is not 1. It has to be cosine squared plus sine squared to be 1. Sometimes students see that and they say, oh, well, it's -1. No, it's not -1. It's got to be sine squared plus cosine squared equals 1. That's the identity. But it is the difference of two perfect squares, so we could factor that. And if you really look ahead, that's going to be a positive thing because one of our factors is going to be cosine of x plus sine of x. And what's going to happen?
It
Cancels with that sine x plus cosine x in the denominator.
That's it too.
So you have cosine of x minus sine of x over sine cosine. I really don't know of anything else that we can do.
It's separate the fraction.
You could. That's true.
And then you get cosecant minus.
Go up to the top.
Yeah, Allie's right. There's, a good trick is at this point we could take each term in the numerator and put it over the entire denominator. So cosine of x over sine cosine minus sine of x over sine cosine. And the cosines cancel, which leaves me with 1 over sine, which is cosecant. And on this one, the sines cancel, so I'm left with 1 over cosine, which is secant. And that was what the other side was originally, so that would work. If you didn't do that, you could have gone back to what we had originally found a common denominator and combined those, it's a single fraction, and you would have gotten this, and the cosine x minus sine x over sine cosine. So you get away with it. Just make sure you choose some way where you've actually shown the two sides are. All right, anything through 12?
I mean, you still need it.
Anybody need 10? Everybody good? All right. Any other questions through 12? Wasn't 9 nice? That was like
Took me like 2 seconds.
I know. It's on that left-hand side. Oh, if I factor that as a difference of squares, sine squared plus cosine squared to 1, not done. All right, anything through 16, 15? All right, 15, we have secant minus tangent equals cosine over 1 plus sine. We can go ahead and just rewrite this left-hand side. Secant minus tangent is really just going to be 1 minus sine over cosine. Everybody accept that? Because secant is 1 over cosine and tangent is sine over cosine. So they have a common denominator, and you can combine them as a single fraction. Then what?
I did the right, but I did the conjugate, so I did the conjugate.
Conjugate, all right. So we'll multiply by 1 minus sine. And you'll notice that we only have to do it on one side. We don't multiply both sides by their respective conjugates. One side will be enough, because now on the right-hand side in my numerator, I'll have cosine times 1 minus sine. And in the denominator, I'll have 1 minus sine squared, which is cosine, which then, or cosine squared,
Cancel.
which then cancels with the cosine of the numerator. And then the two sides are equal.
13.
And there's probably other ways of doing that. I mean, you probably could have not even bothered changing the left-hand side, because at this point, once I have 1 minus sine over cosine, then I could split it apart as 1 over cosine, which is secant, and sine over cosine, which is tangent. And that was what the original left-hand side was. Which one, Alex? Number 31.
Basically. Just have to figure out a way to play. Pretty good stuff.
This one would work by changing everything to be in terms of sine and cosine. I just don't think it's necessary, because on the left-hand side, there's a GCF, so I can take out cosecant. And then, what is cosine squared minus 1? Negative sine squared times cosecant, which is 1 over sine. And then, so you have negative sine left. Anything else through 16, 14?
Oh, yeah. Are we learning stuff today?
Yeah, we'll talk a little bit about equations, but we're going to do much more of it on Monday. We also have last night's homework to go over. All right, again, I can change everything to be in terms of sine and cosine, but look for the easiest things that you can. Here, I could separate this out as cosine squared over sine squared. And then tangent squared over sine squared. What's cosine over sine?
Cotangent squared.
Now this one, tangent squared would be sine squared over cosine squared. And then all of that over sine squared. You could, or just end up dividing. I mean, sine squared over cosine squared divided by sine squared would be the same as multiplying by 1 over sine squared. So, those cancel. And then what's 1 over cosine squared?
Now, the one method was simpler too.
And that's what the right-hand side is. Equal to. That'd work. But again, if you changed everything to sine and cosine and it took you 2 extra steps, who cares? You know, you still get there in the end. Right?
Oh, yeah, 17. The only one I could get.
The only one. Yeah. Still didn't put that either.
Did you get it?
Yeah, I think this one's pretty hard. You really have to maybe take a breath real quick and think long term about some things that, you know, if you were to try and get a common denominator or whatever, that could eventually work. But if you really think this through, what if I multiply by the conjugate of 1 minus sine? What am I going to get? It would be 1 plus sine, which then becomes cosine squared. And when I cancel cosines, then now I'm going to have a common denominator. This cosine will be in the denominator for both. So if you can kind of reason that out and look ahead a little bit, then it does make sense to rationalize just this denominator.
So you can rationalize just like one piece of the whole side?
Sure. Because all I'm doing is taking that one fraction and multiplying it by the same thing on top and bottom. That's allowed. All right, so I have 1 minus sine over cosine plus, now what I have is cosine times 1 plus sine over 1 minus sine squared. And 1 minus sine squared is cosine squared. And that cosine cancels with one of those. Okay? Now we have a common denominator, right? And so we're ready to add these two fractions together. So I'll do 1 plus 1 is 2. And then negative sign plus positive sign cancels out. So I get 2 over cosine, which on the right-hand side was 2 secant, which is 2 over cosine. Two sides are equal. You can. All I gotta do is show the two sides are equal.
So, how about 18?
Yeah.
All right, for 18, I'm going to go ahead and put sine over cosine for tangent. And 1 over cosine for secant. And I probably won't go through this. It's very, very similar to number 17 in that I'm just going to rationalize that one denominator. And then it's really going to work like exactly the same from there. Because that would become 1 minus sine squared, which is cosine squared, which cancels.
Okay, so what I did was I got them to have the same denominator, so I multiplied that sine.
Yeah, that's fine.
Is that okay?
That's fine,
It's still fine.
as long as I get you there. All right, and then 19. I'm going to replace those secants with 1 over cosine. And then I have a compound fraction. And what's the common denominator? Cosine. So multiply everything over here by cosine. 1 over cosine times cosine is 1. 1 times cosine is cosine squared. 1 over cosine times cosine is 1. And 1 times cosine is cosine squared. And then sine squared, 1 minus cosine squared.
Oh, I changed the right side to cosine squared minus 1 instead of 1 minus cosine. So I was playing along.
All right. I think I'm good with those. So let's go to last night's homework, which was 2 pages from that. All right, page 450. All of those were odd, so all the answers were in the back of the book, so hopefully you check those. Any of those that you didn't quite understand? 30? 39? All right, 39, we have the inverse tangent of the tangent of negative 3 pi over 8. And of course, our inclination is that those two things cancel each other out, and we're just left with negative 3 pi over 8. But we've got to check to make sure that we're in the right quadrants. So for inverse tangent, what quadrants do we have output values from? All right, first and fourth. So from negative pi over 2 to positive pi over 2. Is negative 3 pi over 8 within that? Yeah, because negative 3 over 8 is going to be in the fourth quadrant, but not all the way to this, which would be negative 4 over 8. So we're in the fourth quadrant. That's fine. So we can accept that.
Can you do 41?
41? right, same kind of thing. Again, we would kind of anticipate that those would cancel each other out, and we would think, well, my answer would be 9 pi over 8. However, in what quadrants is inverse sine defined?
First and fourth.
First and fourth. Where is 9 pi over 8 located?
Second.
Third, right? Okay, so we can't use 9 pi over 8. So we have to reason this out then and say, all right, in the third quadrant, what do you know about sine? It's negative. So of these two quadrants, sine is negative in the fourth quadrant. So I've got to pull my answer from the fourth quadrant. And the easiest way to make that happen is just put a negative pi over it.
Wait, but how do you know it's negative?
It's got to be in the fourth quadrant.
I don't know why, why, like, how do you know that?
Oh, because its coterminal angle in the fourth quadrant would be 15 pi over 8. And that's not between negative pi over 2 and pi over 2. So I just make it negative pi over 8 to ensure that it's within those range values.
Can you explain 47?
Right, this is telling me to find the angle whose tangent value is 4, and then once I have that angle, find the tangent value. So if I'm finding the angle whose tangent value is 4, and then using that angle to find the tangent value, I'm just working in circles right back and forth.
Okay, but how do you know, like, what if it wasn't? I guess that's not the units, right?
Facts.
Yeah.
Well,
Yeah, but remember for tangent, our domain is all real numbers. Our inverse tangent, our domain is all real numbers. We're not restricted to be between negative 1 and 1. Yeah, there's a lot to remember with inverse. 11.
11 was on the next page. Oh, wait.
Yeah.
15.
Oh, yeah.
All right, so this one is saying the inverse sine of negative 1. Where is sine negative 1? Where does that occur? Down here, right? Which we would normally say 3 pi over 2. But remember, inverse sine is defined between negative pi over 2 and positive pi over 2. So instead of using 3 pi over 2, I'm going to use negative pi over 2. They're the same, they're coterminal. It's just that for inverse sine, it's got to be between those values. All right, let's go to the next page, which was page 457, 15, 11. All right, for this one, can we evaluate inverse cosine of negative square root of 3 over 2? I mean, is that one of our special values? Yeah. Okay. So, at what angle on the unit circle is the cosine value negative square root of 3 over 2? Pi over 6, but we got to be in the second quadrant, which would be 5 pi over 6, and second quadrant's defined for inverse cosine. So all of this just became 5 pi over 6, and then now we're going to take the tangent of 5 pi over 6. And then the second quadrant, what do you know about tangent? It's negative. The reference angle here is 30 degrees, and the tangent value is 1 over the square root of 3. So we get negative 1 over the square root of 3. They rationalize it. Square root of 3 over 3. That'll work. Either way, it's fine. Any other questions on 35? We have the inverse sine of the cosine of 3 pi over 4. Again, we can evaluate cosine of 3 pi over 4. 3 pi pi over 4 is in what quadrant? What do you know about cosine in the second quadrant? And what's the reference angle? And at pi over 4, the cosine value is? Okay. And then now we're trying to find the inverse sine of negative square root of 2 over 2, which, when does sine take on negative values? In the third or fourth quadrant, but because it's inverse sine, we're going to choose the fourth quadrant. And the angle where sine is square root of 2 over 2 is pi over 4. But if I want the one down in the fourth quadrant, I'll just choose negative pi over 4. Anything else? All right, well, good. What we'll do for the next few minutes is let's just kind of start talking a little bit about solving equations, and that way on Monday we'll be ready to really jump into a good number of examples, which we've already done, because on the class starter today, you really had 4 very simple trig equations. And, so the idea is very similar to inverse trig functions. That's why we did inverse trig functions yesterday. But it really kind of sets the tone for how we're going to solve trig equations. It's just that for solving trig equations, we're not restricted to particular quadrants anymore like we are when we're evaluating an inverse trig function. When we're solving an equation, we want all the answers, wherever they are on the unit circle. So, we're solving these trig equations, and, it's going to make use of the idea of an inverse trig function, but without the restrictions. So in a lot of ways, maybe even that solving trig equations is easier because you're not having to go through that whole process of what quadrant, where is it restricted, and all that. Right? So these are the steps that we're going to follow when we're solving trig equations. That first step in solving a trig equation is one that can make some of these equations a little bit more challenging. But it's really important that you take care of this. It says that you have to make sure that you have only one trig function in your equation. And you oftentimes will have to use identities to do that. We may have an equation that has a sine and a cosine in it. But what we have to do before we attempt to solve it at all is we have to make sure that we have only one trig function. So instead of having sine and cosine, then we need to have only one, only sine or only cosine. And we can use some identities to help us rewrite it so that there is only one, but we've got to make sure that we do that. It might also require us to do some factoring. Maybe by factoring, then we could split the equation up like we had on the class starter, where one piece has cosine, another piece has tangent, but we're are solving those pieces separately. But you got to have only one one trig function. And once you have that trig function, then like we would do with any other kind of special equation, we want to get that function by itself. So when we solve absolute value equations, we get the absolute value by itself. When we solve radical equations, we get the radical by itself. And so the same thing here, when we want to solve trig equations, get the trig function by itself. And then from there, we're going to ask ourselves, where on the unit circle is there an angle that has that specific sine value, or that specific cosine value, or that specific tangent value, or whatever. I say in that case, we're going to kind of use inverse trig functions in the sense of freeing that variable up. So when I have sine of x equals a half, then I'm really thinking, all right, well, when does x equal inverse sine of a half? Because that's going to get that x by itself. It's just I'm not going to restrict myself to a particular quadrant like we do for inverse trig functions. And then from there, we find all of our answers, including any coterminal answers. to the angles that are on the unit circle. And we'll hold off there. You've done 4 examples for homework, we call the class starter already. We'll look at some more advanced ones on Monday. Just keep in mind that next week we're going to do equations on Monday. We'll go over that homework on Tuesday, and we'll talk about adding and subtracting, or the addition and subtraction formulas, which are a few more identities that you'll have to have memorized. And then we'll go over that on our homework on Wednesday, and then review Thursday and test Friday. I won't be here next Thursday or Friday, but your Thursday you'll be going over the study guide together, working on the study guide together, and then your test is Friday.